Hi there and welcome to the screencast for Workshop 7. So we're starting classification today and I'm going to start by installing some packages. So classification is essentially the same as prediction, the difference being that our outcome variable, our target, is a factor variable. And the tools that we'll be using for this are namely, of course, parsnip, the Tidy Models framework, do require the outcome variable to be a factor, so a categorical variable is not enough. So we're going to start by running this first code block. And you can see that I haven't installed Tidy Kda. So Tidy Kda is a package that I've created to wrap the kernel smoothing package, the KS package, in particular the KDA function there, so that it works in the Tidy Models framework. And that's brand new, so you can install it using this command here. So I'm just going to copy that down to the console area and run that. And that will install the package from my GitHub. So it's also prompting me to update a bunch of packages. Let's have a quick look through this. Do I want to bother? I don't think those are particularly useful for me today, so I'm going to say none of those updates, please. So it's going to build the package. There we go, and then install it. Right, so we should be underway now. And so we're going to look at two examples. The first one is to do with 3 separate synthetic data sets, for which we have both training and artificial test data. Notice that I am telling it that the group variable in these CSV files should be a factor. Okay, so I'm using a column specification in the read CSV in order to tell it it's a factor, in particular to tell it it's a factor and specify the level. So by default, any categorical column, so any column that contains basically string data, a bunch of labels or whatever, will be interpreted as a character vector. And if we want it to be interpreted as a factor, then it will go ahead and do that for us by specifying group equals col_factor in the column types argument. I'm specifying the levels here just to make sure that the levels are all in the same order, because there's no guarantee. So by default, read_CSV, when it creates a factor, will create a factor in the order that it appears in the file, and these have been randomized, so it's not necessarily ABC. So that's why that's happening. Okay. So we could start by having a quick look at what these look like. So for example, we could use skim. It's in one train, and we can see that there's no missing values, it's all complete, and that we have a grouping variable with 200 A's, 200 B's, 200 C's, and then what looks like normally distributed numeric variables x1, x2, and x3. And presumably then the test set will look somewhat similar. Okay, hopefully our test set and our training set are somewhat come from the same population. Otherwise it's going to be very hard, of course, to do predictions on the test set if it comes from a different population. But these seem as though they have a similar mean, similar distribution, and a similar distributed number of different classes. And we could do the same thing for the other ones. Okay, so if we have a look at sim 2, then again we see that they're equally, so we have equal counts of A, B, and C, and again we have roughly symmetric distributions here. And sim 3, again, same type of thing, right? Equal counts of A, B, and C again. So because there's equal counts of A, B, and C, there's no advantage of predicting any particular class. So for example, if the observations were dominated by one class, so say in our training set we perhaps had 600 observations and maybe 500 of them were of class A and only 50 of class B and C, then of course the default predictor, the default classifier being everything is class A, will get it right for 500 out of 600. So we'd get a very high classification rate of 83% without even trying, right? Obviously we'd get B and C completely wrong, but we'd still get a classification rate of 83%. So when you do have imbalanced classes, you've got to be quite careful about your about the way you do predictions, and in particular about what sort of your baseline classification rate should be. So if you've got equal classes, then your baseline classification rate should basically be a third, right? If you've got 3 classes, right? Because if you just randomly choose A, B, or C, then you'd get it right on average 1 out of 3 times because there's only 3 classes, right? So for example, we could predict everything to be class B, and we'd get, on the test set, we'd get 100 out of 300 of them completely correct, and we'd get 200 out of 300 completely wrong, right? But nonetheless, we should be able to do at least as good as 1/3 classification rate by default. So, we'd be expecting any classifier to do better than that. Okay, let's have a look a little bit more graphically at what these distributions look like, because that will perhaps give us a feel for how the different classifiers are going to work. So let's start by having a look at the first one, sin1.train. And we're just going to start with perhaps looking at the first 2 numeric variables coloured by the grouping variable. Okay, need a comma there. Okay, and so what I notice here is that within each group the distribution looks about the same. So it looks to be some sort of a multivariate normal distribution, right? It's mostly, they sort of look elliptical shaped, and if they look elliptical shaped, then often a multivariate normal is appropriate. But there's clearly shifted centers. Okay, so this is going to work well for linear discriminant analysis, because even though there's quite a bit of overlap between these groups, nonetheless the underlying distribution within each group is the same and can probably be modeled using a normal distribution, and the only real difference between the groups is the location, the center. And that's the exact assumptions that LDA makes, that linear discriminant analysis makes. It assumes that the distribution of the numeric variables within each group is a multivariate normal that has the same scale, or the same standard deviation, if you like, multivariate version of, so same covariance matrix within each group. And the only difference between the groups is the location, the mean. And we see the same thing if we look at the third variable as well. So if we look at x1, x2, and x3, again we're getting that same shape. Okay, so it seems here as though LDA is likely to do well on this data set. Let's have a look at sin2. So we could look at x1 and x2 again. Okay, in this case, clearly the means are the same, right? They're centered all at the same point there, which is about at 1, 5. They're all centered at the same point, but the spreads are clearly different. So linear discriminant analysis, which assumes that the spreads in each group are the same, is going to do poorly here, because that's a really bad assumption to make. Further, linear discriminant analysis assumes that there's a difference in center, and clearly in this case there's not a difference in center, so again it's going to do poorly. So some other techniques are going to do better here. So for example, kernel discriminant analysis will do a lot better here, because that makes no assumption about the distribution within each class, and in fact fits a kernel density estimate to that, so that will do quite well. And so will naive Bayes. So naive Bayes assumes that the predictors are independent, and in this case they look as though there's independence, right? Within each class there's no trend. Okay, let's look perhaps between x3 and x2 as well. Yeah, there's still no trend, right? So so naive Bayes is going to fit either a density plot, a density estimate, or a normal distribution within each group, but just univariate. So just a univariate normal for x3 and a univariate normal for x2, and then it just multiplies them up and that's going to work quite well for this example, because the assumption that it's making that each of the predictors are independent is in fact true. So when we make a strong assumption, and that strong assumption is true, then the method is going to be quite powerful. What about the third data set? Okay, so the third data set is clearly not independent, right? There's a very strong relationship within group C. So naive Bayes is unlikely to do well here, because it's going to assume that x1 and x2 are independent within each group, and clearly they are not. Similarly, linear discriminant analysis is going to perform poorly here, because it's going to assume that the covariance within each group is the same, and clearly they're not, right? It looks just to me within the A group they're probably independent, but within the B and C groups they're not, right? So they have very clearly different covariance. So assuming the covariance is the same is going to do really poorly. Kernel discriminant analysis is likely to do well here, because it makes essentially no assumptions. The disadvantage with kernel discriminant analysis is that you do need a lot of data points in order to make a decent go of estimating the distribution within each class. Typically, so Tidy KDA is set up that it will only work with 3 covariates. If you go any more than 3, then it will just not function at all. It will spit out an error. I think I probably can extend that to 6. But after that, it's just getting too high dimensional. So this is known as the curse of dimensionality, and we'll talk about that in lecture 7. Right, so we're going to have a look. So let's just sort of refresh our thinking. We'd expect LDA to do well on SIN 1, because the distribution within each class has the same covariance. The only difference between the classes is the location, which is the exact assumption that LDA makes. We'd expect that naive Bayes should do best in the second one, because they are in fact independent, and that's the assumption that naive Bayes makes. And because neither of those assumptions hold for the third set, we'd expect that the most flexible technique should do the best, which is kernel discriminant analysis. Now my feeling is KDA is probably going to work quite well in all of them, but LDA may work best in SIN 1, and naive Bayes may work best in SIN 2, but we'll see. Okay, so we're going to use our typical setup of a tidy model. So we create a specification for our LDA, and then we fit it using the fit problem. So this is exactly the same setup as we would use for a prediction problem. The only difference is that the mode is classification. And of course, because linear discriminant analysis only does classification, the mode is set automatically for us. So let's run this code block. Okay, we could have a look at the object that's spat out, and you can see that it's a parsnip model object like always. Okay, we could use extract fit engine to get the actual underlying LDA model. You can see it's estimated the prior probability in each group as being 1/3, because of course it uses the group frequencies. It's estimated the group means, and you can see that these differ quite a bit, which of course is what LDA is looking for, and it's computed the linear discriminants. Okay. Essentially these form a transformation from the original variables, or I think it's the scaled version of the original variables, onto the axes that define the linear discriminants. Okay. We can then, so based on this fit, which has been trained up on the training data, we can then augment it with the test set in order to get our predictions, and then use the confmat function to get a confusion matrix. So this comes from yardstick as per usual. And so there's our confusion matrix, and you can see that the big numbers are all on the diagonal, which is where the truth and the prediction are the same. And the smaller numbers are on the off diagonal, where of course we're getting things wrong. So we could compute the accuracy would just be 83 plus 73 plus 80 divided by the total. So 83 plus 73 plus 80 is what? It's 236. 236 out of 300. Okay, so that's about 75% near enough. Okay. obviously we can compute that with the computer, so the accuracy function from Yardstick will compute that for us. And so it's 78.6%. There you go. Okay. So we're getting it wrong about 21% of the time. So we could do the same thing for the other two data sets, and we'd expect, of course, that LDA does worse for these. Okay, so we could have a fit LDA2. It's going to be, we're going to take our LDA model spec. Okay, we don't have to create a new one because, of course, that's just generic, right? We haven't fitted it to data. That's what we're doing here. So we're going to fit the outcome variable, so group in terms of all predictors. I could just copy this, couldn't I? But I'm just going to use the second training set. And then I could have a look at the third one as well. And if we have a look at these two objects, then you can see here that the group means are quite different for this one. Even though when we actually looked at the data, the group means were not different at all. Right, if we actually had a look at, so here's what the actual true groups are, and here's the group means estimated with LDA, okay, and so you can see that these are actually, this one is miles out, okay, they should all be the same, right, but of course LDA is wanting them to be different. Okay, and we can have a look at fit LDA 3 as well. Okay, and again it's estimated different means, even though the means in the third group were again the same. Okay, so we could have a look at prediction. Okay, so grab the prediction line. Do that for each of them. And then evaluate the predicted performance. Okay, so we could just run accuracy, or we could run our confusion matrix. Let's run both just so that we can get sort of a little bit of muscle memory. All right, so there's the prediction matrix for LDA2, and you can see that it's very poor prediction, right? So on average, so we're only getting, what, 98 correct out of the 300, so our predicted performance is about a third here. And again, we're doing just a little bit better than a third here. In particular, we're getting Group B much more wrong, right? We're saying Group B is mostly Group A and Group C. So we're doing very poorly here. So let's summarize them. Let's work out the accuracy. So truth equals group. So you can see here that the accuracy of the first one is only 33%, which of course is no better than guessing. This is only a tiny bit better than guessing. And the last thing I'll say is that we can actually look at LDA2, and we've actually got the predictions for each class as well. So while we've got the predicted class, okay, that just corresponds to whichever one of these is biggest. So you can see here that actually there's really nothing distinguishing these, right? It's a tiny, I mean, for this observation here, B is the best, but only just, right? There's not much in it, and some of the others are even closer. Look at this one. Right? What can we, we're using the third decimal place in order to say that it's of class A. Really, the answer should be we have no idea which class it is. Okay, which makes sense. We've basically got no information from this, and we'll see a similar thing with LDA 3, right? And that most of the classes we're very, very unsure about our classifications. Okay, so let's just write a bit down here. So based on what we know about the assumptions of linear discriminant analysis and our EDA, does the classification performance make sense? So yes, it makes sense. The assumptions that LDA makes are that the distribution within each class is a multivariate normal with common covariance and differing centers. This works for SIN1 as that is what we see. It doesn't work for SIN2 or SIN3 as the covariance within each class are clearly not the same. Lots more spread. So differing scales in SIN2 and differing amounts of correlation in SIN3. Where the LDA assumptions fit, i.e. SIN1, the classification is reasonably good. Where the assumptions do not fit, we're basically guessing, doing no better than guessing. Okay, so we're now going to look at the other two methods, naive Bayes and KDA. So we use naive Bayes as the specification. It's got a capital B because Bayes, of course, is a surname. And we use the naive Bayes engine. So there's a number of different engines that implement naive Bayes, and this is the one that sort of corresponds best with the lecture material and so on. But you can try another engine if you like. Okay, so by default, the naive Bayes is going to be assuming that each of the predictors, so x1, x2, and x3, are independent. So that's going to work for the second data set, so SIN2, but it's not going to work for SIN1 so well because, of course, there was a trend there. We saw a trend on the x1 versus x2 data set, so there's correlation between x1 and x2. So assuming independence is a silly thing to do, but it might not be too silly, we'll see. And it won't work at all well for the third one, where there was very strong correlation in the x1, x2 plot for the group C. But it may work okay for SIN1, and it will certainly work well for SIN2, where they were in fact independent. And then by default, within each of those groups and each univariate variable, so to model x1 within the A group, it's going to use a kernel density. You can tell it to use a normal distribution instead if you wish. There's some guidance in the notes about that. Right, so let's set up our specification and fit our model. And we see that we require an additional package. So let's install that one. So install.packages naive Bayes, and this is a sort of a nicer way that the tidy models framework works, is it doesn't actually have dependencies on any of the underlying modeling functions, which means that when you install tidy models, you don't get 300 models installed, 300 different packages installed, which then makes maintaining tidy models extremely hard. Instead, it basically calls the functions within other packages, but doesn't actually using the rcall functionality, which means that it doesn't have a dependency on those other packages, and then of course it just tells you if you need to install it, which we have now. So let's have a look at this model object fit NB1 just to have a feel for what it spits out. So again, it's a parsnip model. Okay, we'd use extract fit engine to get the underlying naive Bayes thing. You can see that it's estimated the prior probabilities exactly the same way using the frequencies, and then within each class we've got x1. Within the A group, it's fit using a density. So it tells you some information about the density, plot that it's fitted, and then within group B it's fitted different density, and within group C it's fitted different one. And you can see that the ranges of X are different in each case. Okay, because of course they're shifted in terms of x1. And then it's got x2 in terms of A, x2 in terms of B, x2 in terms of C, and then x3 in terms of A, x3 in terms of B, and x3 in terms of C. If instead we want to fit a normal distribution within each group, then I'm pretty sure we do it like this. So we alter our specification via set engine, I think. So we go engine equals naive Bayes, and then we add in use kernel fault. I think that's what it is. Let's have a look. So let's, and then we go run fit. So I'm doing this from memory, so hopefully, use kernel is not the argument. Is it just kernel maybe? It must be null or a character vector. So I am going to look up the notes for this. So let's jump onto Stream. Look at the study guide for classification. Naive Bayes. Okay, let's see what the setup is. So here's it's fitting a Gaussian, so let's have a look. Use kernel, the no underscore, there we go. That's how I got it wrong, so let's specify that there. So now if we have a look at this object, you'll see that we have in fact it's got our prior probabilities the same, but now we fitted a Gaussian for, in x1, a separate Gaussian in each group. So you can see that the standard deviations are about the same. You remember that SIN1 of course had the same standard deviation or the same covariance within each group. That's why LDA works so well, so that makes sense, but the means do differ of course. Okay, so that's how you do it if you just want to use a normal distribution. Generally, there's probably not all that much advantage. So it's it would be technically it's more powerful if the data are in fact normal, because of course fitting a the true model, a normal distribution, to the data, if that's what it is probably a better way to go than fitting a flexible density estimate. But a density estimate fit on a set of normal data is actually going to estimate the distribution reasonably well anyway. So there's probably not much advantage. You'd have to be really certain that the distribution within each variable within each group is in fact normal before I tried this trick. Okay, KDA then. So we've got a spec for a KDA, and then we fit that. It takes a little while because of course we are running in so we are fitting a three-dimensional kernel density estimate. We could have a look at it if we want. It's going to have a lot of information. Okay, so it's a parsnip model object and it's got lots and lots of junk inside it. So the estimate there is basically so what it does is it gets a huge grid, and it'll have three of them, one for each class. You can see here this is the density so this is the height, if you like, of that density distribution in 3 dimensions. And so it's some huge object, and then we've got the grid dimensions here, and then we've got the data all stored. So there's a lot of junk stored in that KDA object. Okay. Right, so now let's get rid of that. Now we can do prediction on each of them. So we're predicting, we've got predictions for naive Bayes, we've got predictions for KDA, and then I've bound them all up to give an overall prediction data set. So if we have a look at predict 1, we've got 900 observations, so we've got the LDA observations, LDA predictions, and then further down here we're going to have the, once we get past 300, we've got the naive Bayes predictions and so on, right? So now we can group by the model and then compute the accuracy. So there we go. You can see that LDA has in fact done best, but the others aren't far off. Okay, KDA of course should do reasonably well anyway because it's quite flexible, and it just doesn't quite do as well as LDA because when we estimate each of those density distributions, we're not using a common pooled estimate across all the groups, which LDA is doing. So LDA is assuming that the covariance in each group is the same, so it can pull them together when estimating the covariance. Whereas KDA can't do that. All it's doing is doing a flexible density estimate within each group. Naive Bayes also does quite well. So even though the independence assumption is clearly wrong, right? When we looked at the data, there was clear correlation there. Let's have a look again. Remind ourselves. So it's this one here. Clear correlation. So assuming independence is definitely going to bias our results, but nonetheless, by doing so, when you actually fit the model, your everything is easier in terms of the model fitting, right? Because you're just estimating a distribution in one dimension, right? You're estimating a bunch of univariate distributions and then multiplying them up. So the fitting side of it is going to be really easy to do, therefore would have lower variance. So while you're introducing bias because you've assumed independence when independence does not exist, nonetheless, you're doing okay due to that reduction in variance. And in this case, it's just because while they're not independent, they're not too bad in terms of, they're not too highly correlated. Okay, so the introduction of bias isn't too bad. Okay, so let's just make a note. These all make sense. We'd expect LDA to do best on these data. In naive Bayes, still does okay, while it will be biased as the predictors are not independent, they're correlated, they're not strongly correlated, so the amount of bias introduced by assuming independence is perhaps not too much when we consider the reduction in variance that is likely, as it's much easier to fit univariate to estimate distributions within each class. Okay, so let's do the same thing for SIN 2, SIN 3, and compute accuracies and so on. So we can just take the code that we've done before. Grab our fits, just grab that block. We can use the same specs, of course. We don't need to split them out, I don't think. Right, so we're going to get fitting the second one. So there's our model 2, and then we'll do prediction as well and bind them up. Okay, so let's run all that. And then finally do our accuracy. So group by model. And then compute accuracy truth is going to be our grouping variable, and our estimate is going to be our .pred class. So you can see here for the second data set, KDA is by far, oh no, naive Bayes actually takes it. And that makes sense because in this case, they are independent, right? So the assumption of independence allows us to then, instead of fitting a kernel density estimate in a multivariate three-dimensional kernel density estimate for each class, we can fit univariate density estimates for each class and then multiply them up. And so we get much more power by using the naive Bayes. We can use our data a little bit better. And then same thing for the third data set. So let's go through and change all the 2s to 3s. Probably should have find and replaced in that selection, shouldn't I? Right. So I could, if I select it and then go Control F for find, I can click in selection. So I could have, done sin2.train and just replaced it with sin3.train and got it all done all at once. Possibly even just replace 2 with 3 would have done the trick. Right, so let's run that code block. So what would we expect for this one? We would expect naive Bayes to do poorly because we have strong correlation, right? You remember in group C there was very high correlation between x1 and x2, and of course it does do poorly. Oh, hang on a sec. Haha, I should have replaced, shouldn't I? Because I missed to. That's better. Right, so naive Bayes does poorly, LDA does poorly, of course. Again, because the means are the same, the covariances are clearly different, so the assumptions of LDA are way off. And KDA here is by far the superior model. Okay, so for sin 2, so for sin 1, we've already discussed. LDA works as the strong assumptions it makes constant covariance differing means hold. For sin 2, naive Bayes works best as the strong assumptions it makes independence hold. And for sin 3, KDA works best as the strong assumptions of the other two models do not hold. So the more flexible model works best. Okay, so do be prepared to examine your data sets and get a feel for which techniques are likely to work best. Particularly if the data set is quite small like this, we only have 3 predictors. It is quite easy to do your EDA and look at those model assumptions. Obviously, this is a synthetic data set that's been set up for this purpose, right? We're now going to look at a real data set where this is not the case. Okay, there's some odd character there. I don't know what that is. Hopefully that won't cause issues for you. Right, so let's read this data in, and we're going to split it into 2. Okay, into a training set and a test set. And now we're going to start assessing the shape of each predictor. So we're going to do this in the same way as we did before. We're going to go and grab all of the numeric variables, pivot them longer, and then do a density plot with to assess the distribution of each of them. Okay, so for example, do they look normal? Right, if they look normal, so if you just look at the univariate distribution, if you've got a multivariate distribution, if you look at it in just one dimension, it looks univariate. So you can see here that this is not the case in some variables. So K, which is presumably potassium here, and barium and iron don't look strongly normal. The other ones maybe aren't too bad. So LDA maybe isn't going to work terribly well here, although it's only a few. We can assess balance. So is there balance? And we see that there very much is not balance in the test set in particular. Okay, it's largely dominated by building windows. So a default classifier which says all glass types are building windows would in fact do quite well. We'd get it right 42 out of however many of these there are here. So there's 42 and there's another 14 there, isn't there? No, another 12 there. So 42 out of 56. Out of 54 rather. So we do quite well just by saying everything is a building window. So that should be our sort of baseline. There we go. Right, so let's have a look at these now broken down by class, because of course the thing that we're really interested in is, can we predict the class from each of these? So is there, for example, some differences within each of the covariates in terms of the class? So let's we could try coloring by window type. So what's the window type called? Type. And there is some differences. So for example, these two peaks here in the magnesium are from the building windows and the vehicle windows, whereas the other glasses look quite different in terms of magnesium content. And there's maybe some shifting here in terms of the tableware and the container glass seem different, and perhaps the building windows are slightly different in terms of calcium content. Again, with the barium, building windows tend to have very little barium, and there is some differences in sodium as well, and aluminium. So maybe there is some information here about building types. So this one here seems to be picking out the tableware ones quite well. We could also look at multivariable plots. These can be quite tricky when you've got so many variables. So we've got 9 predictors here. But we could try the ggpairs function in ggli. So we'll load that. You may have to install that if you haven't already, so you can just use ggpairs on the data set that we have here. So glass.train. So let's see what it does by default. It takes quite a while to run and set up all the plots. And so it makes a big grid. So in this case, it's going to be a 10 by 10 grid of each of the 10 variables. Yeah, there we go there. So these are our univariate summaries down there, and here are the scatter plots. And what we're really interested in here, this is correlation up here, which isn't quite so interesting, although that would help us say something about whether naive Bayes is going to work well, of course. So naive Bayes will be assuming that all those correlations are 0. We could add to the mapping argument to color by type, and it'll color each of those points by the different types, glass types. There we go there. So we can see that there is some differentiation of the classes, but not a huge amount. So this is going to be hard to classify. So you can see that there's some differentiation here in the pink versus the red. The greens do look a bit different in some of them. Maybe the blues are clustered in the middle here. So there's some differentiation, but it's quite hard to see. So it's probably going to be quite a hard data set to cluster. And it's not really, I mean, I presume that LDA isn't going to do great because although maybe it won't do too badly. The normal distributions, well, it probably won't do too well because the covariance in each group is obviously not the same, right? So we've got a very spiky distribution in the blue, but a very spread out distribution in the browny colours. So we wouldn't expect it to do fantastic. But nonetheless, it might be trading off a bit of bias for variance, right? So introduce a bit of bias by making the assumption that the covariance in each class is the same when it's obviously not. And the advantage of that is that you can reduce the variance in the estimate. And we do quite well. So 87% classification rate on the test set. We could have a look at the confusion matrix here. Okay, so maybe this isn't as great as we thought because it's getting all of the window vehicles, there's only 3 of them, it's getting them wrong. It's saying that they're building windows. So it's doing well just because it's basically been dominated by building windows. Okay, it is getting the headlamps mostly correct. It's getting all the tableware correct. Half of the container, there's only 2 of them. Correct, it is saying a couple of building windows are containers, but overall it's doing reasonably well. So let's have a look and try and fit some other models to the same set of data. So we're going to fit KDA and naive Bayes models to this, so we'll just grab this data block here. And we will update it accordingly. So let's try, so we're going to do .lda, we're going to replace it with .nb. Okay, and then we're going to do naive Bayes, aren't we? And we're going to do engine equals naive Bayes. Oops. Right, so there's the naive Bayes estimator. Okay, so that's 85%. Not terrible, but not as good as the other one. Let's have a look at the confusion matrix. Again, it's getting all of the window vehicles wrong. And it's also getting all of the tableware wrong. So it's saying the tableware are either container or headlamp. Okay, and we can of course also do KDA as well. So again, if I control F to do replace and do replace NB with KDA. Okay, and then of course do discrim kernel. Let's try that. Then of course when I try this, it immediately gives me an error. And the error is that X should have at most 3 numeric predictors, right? So KDA requires at most 3 numeric predictors. So we'll have to choose them. So this is where we can use our EDA. So if we go back maybe to this one as a starting point, and we look at these and say, well, which variables, because we can only choose 3 of them, which 3 might we pick in order to do best? And the first one I'm going to pick is sodium, just because there is some differentiation here between the green, the red, the brown, between essentially all 3 groups. So I'm going to choose sodium. And then maybe aluminium. There's reasonable there. And then possibly, I guess the hard ones to differentiate here, maybe the brown ones. So can I pick one that differentiates the brown and the red a bit better? Maybe calcium? So let's go for aluminium, for sodium, and for calcium, I think. we'll try that and see how well that does, and we might switch out for silicon maybe as well. So aluminium, calcium and sodium to begin with. So instead of fitting with all variables, we're going to go with aluminium, sodium, and was it calcium that I was going to do? Calcium. Let's try those three. Okay. 87%. That's not too bad. It's sort of similar to LDA, isn't it? Again, it's getting all the tablewares wrong, but it's getting the containers right, and we're getting one of the window vehicles right. But we are getting the tablewares wrong. Can we improve that? So tableware was the blue curve. So you'd think that we would have been able to do better, do okay with that, with the ones we've got. But I wonder if we want to pick up silicon instead of perhaps aluminium. So let's pick silicon instead of aluminium. See how well we do there. Okay, we do much worse. So that's interesting. I wouldn't have predicted that, but there we go. So now we're getting a lot of the we're doing poor on the building windows, aren't we? We're also getting the tablewares wrong still, and we're getting all the window vehicles wrong. So in fact, aluminium was better than silicon. Let's try swapping one of the other ones out maybe. Let's swap out calcium for silicon and see whether we do any better. So we get a pretty similar estimate. Again, we're getting all the tablewares wrong. Okay, so the disadvantage of kernel of KDA is that you do have a restriction on the number of predictors, and that's due to two reasons really. The first one is well, they're both related really. It's the curse of dimensionality. So to estimate a kernel density in a large number of dimensions is really hard. You can think of a kernel density estimate as being similar to a histogram, right? And so if you've got a histogram in one dimension, then maybe you only need, say, 10 bars to get a good feel for the shape of that distribution. But if you've got two dimensions, you need 10 bars per dimension. So now you need 100 bars. So you're going to need, if you've got 100 bars for your two-dimensional histogram, then you're going to need a decent number of observations in each of those bins in order to get a good feel for the actual height of the bins. So you're going to need, say, 10 observations on average in each bin, so you're going to need 1,000. 10 observations, 10 bins for the first variable, 10 bins for the second, multiply them all up, you need 1,000 records just to fit a two-dimensional histogram. In this data set, we only have 160 observations in the training set. So fitting a kernel density estimate, or fitting a histogram to just two of those variables, is going to mean you only have a handful of, if we had a 10 by 10 histogram fit to just two variables, we're only going to have on average 1.6 observations in each bin. So we're going to have a very crude representation of the histogram. And the same thing applies to a kernel density. It's going to have a crude estimate of the kernel density because you just don't have much coverage of the high dimensional space. And we're only in 2 dimensions. As soon as you go to 3 dimensions, of course, it just gets worse, right? 3-dimensional histogram, if we want 10 observations in each bar on average, you're going to need 1,000. You're going to have 1,000 bins. You're going to need 10,000 observations. Okay, by the time, basically it's 10 to the dimension is a rough guide for how many data points you need. So because we've got 9 observations here, it'll be 10 to the 9 variables would be 10 to the 9 observations required. And of course, fitting the density estimate is going to be really hard because it's such a massively dimensional space, and you're going to have many, billions of points. observations, but also just storing that is going to be hard, right? Because you'd normally do it on a grid, and so your grid, you want maybe 10 to 100 points in each dimension, so you need 100 to the 9 grid points, which of course is far too much memory for your computer to hold. So it's very much a curse in that as you ramp the density, as you ramp the dimension of the problem up, the flexible classifiers find it increasingly difficult to fit anything remotely sensible to the data. So the fact that we have to reduce the number of predictors we use does make it hard, because then you've got to choose which predictors you use, and you don't have a lot to go on for making that choice. You could, so we will look at some other classifier methods, and so you can use a classification method such as like a multinomial regression, for example, which will sort of allow you to kind of rank the predictors, or you could fit a random forest and then look at variable importance, which will kind of get you a feel for ranking which of the predictive variables are most important for defining the classes, and then you could use those on a KDA. So you could do something like that to try and figure out which variables that you might want to use. But it is a restriction. If you in fact do need more than 3 variables to help separate the classes out, then KDA just will not have the information available to it to do its job. Okay, let's knit that document. Maybe we'll write a little bit of a summary down here. So LDA seems to do reasonably well. KDA did about the same. We chose, what did we choose? We chose aluminium, AL, NA, and CA. I think that was the one that did best. Class imbalance is also a problem. Just saying everything is a building window gives a pretty good classifier. Okay, I'll knit that and make sure it all works. Actually, it takes a little bit of time, because of course each of those kernel density estimates takes quite a while to fit. So just a tip for your second assignment, if you are doing a lot of model fitting, then you may want to do the actual model fitting in a separate R script or a separate markdown file, so that you can just run it when you wish, rather than trying to put it all into one markdown file that you then submit, because as you do your write-up about what you did to do your classification or prediction, you don't want to be waiting on the computer to refit all those models just to update the text and check it looking nice, particularly if you've got some if you're just working on formatting or whatever. I'm going to get rid of that. We don't need that output from the KDA there cluttering things up. Let's get rid of that. So that would be here, and I'll just reknit that. Okay,